Okay, so I'm thankful to the organizer once again. The topic what I have chosen to present before you is the flexible polymer-based gel electrolytes for sodium ion storage devices. Uh, आप change करिए हाँ. Before I go to the back. Yeah, before I go to the topic and the discussion, I would like to show you this is the colonial building. This was the office of Lord Mountbatten, the last viceroy, and now it is the office of our vice chancellor, and other offices, administrative offices are there. So in the 1942, the many freedom fighters they have taken over this building once upon a time, and Gandhiji was hybrid devices of different types. So please. Hybrid devices means that how we are going the mixing the two technologies together, and one of the method of the hybrid device is device made up of the hybrid material. So material as such is the hybrid means suppose you have a mixture of the double layer capacitor material and the pseudo capacitive material. So if that kind of material is being used, for example, carbon and MnO2, if you are mixing it, then you are making the capacitor, which is called to be hybrid device. The second type of hybridization is the external hybridization, where batteries and supercapacitors are both together externally used, and it is a parallel combination. And as and when it is being required, this for the continuous run, the battery will be using the battery, but for the peak power requirement during the acceleration, during the climbing to the hill, then supercapacitor works, and then come back to in few seconds to the charging mode, and which serves by the batteries. The third one is very important. This is called internal hybridization, in which the same device, like it is given in the figure, this is one of the example lithium-ion capacitor, in which one side is the battery electrode material, and other side is the supercapacitor electrode material. The electrolyte is common, and so one interface will ensure the power density, and the other interface ensure the continuous energy for the devices or any appliances when it is required. So this is the combination of these two. So this is internal hybridization I'm talking about. You know that lithium ion technology is very popular these days and is still going on in the market. But they have certain advantage, of course, and they have that high energy density. Cell voltage is very high, very low self discharge, and shelf life is also very long. And in size, it is also very so volume specific density. It is also very high, but there are certain limitations that the expensive to manufacture, cost effective, it is not cost effective. Protection, a lot of protection is involved here, and it is highly sensitive to the high temperature. And one of the most important thing that they're costly because their reserves are very limited in the very localized geographical areas. The lithium and the lithium compounds are available, so it is under the control of few countries only. Whereas the sodium is available everywhere, and this is the good alternative because of that. And their reduction potential means electrochemistry is also almost parallel to the lithium, so it can be used. The only problem what we are facing in the sodium ion technology is the ionic radius of the sodium. And ionic radius, because of it is high, we need a suitable cathode and anode for that material. Otherwise, electrolyte is not a problem. Here, Professor Anji Reddy is here, who is expert in electrolyte. So he is from Hyderabad University. So you can collaborate with him. Electrolyte, he is very expert person. Well, so next slide, please. So if we are talking about the hybrid device of the sodium-based technology, one of the important device is the sodium ion capacitor, in which one side of the interface, one side is the activated carbon we have used, which is a capacitive electrode material, and other side is the hard carbon, which is another form of the carbon, which is behaving as a good anode material into electron. If we are making sodium ion batteries, then hard carbon is a good anode material. So this is the combination of the two technologies, one the battery, other is a capacitor, and that's why it is a hybrid device, and this is called sodium ion capacitor. Right? It is working very good these days, but still we have issues and problems. And our lab, in Delhi University, we always focus on to flexible electrolyte based on polymers. Professor Anji Reddy is also in the series of those group, so he is also working on this area. So I am emphasizing now to the electrolyte part of this my talk in this. So the electrolyte actually it is a very important key point, key component of the energy storage device, and we need the characteristics of the devices, electrolytes, and in general should meet these are the following need and requirements of any electrolyte if you are choosing. Then its conductivity should be very high. You know that some of the polymer electrolyte whose conductivity is not very high, from the energy storage point of view, it is not useful material. So you have to be in this order of conductivity at room temperature at least. Wide electrochemical potential window is also required because energy density always also depend on the voltage range. And then high chemical and electrochemical stability, thermal stability is required. And then it should not be toxic, it should be safe. And of course, over and all, that it should be cost effective. Yeah, for our important economy. So I have divided the entire electrolytes which are using into energy storage into three parts. One is the aqueous electrolyte, organic electrolyte, and ionic liquids. These are the three major electrolytes which are being used into the energy storage devices. They have some common problem like self-discharge, bulky design, corrosion. These are the problems with the liquid electrolytes. But there are certain merits and demerits. So next slide, please. Next slide. Yeah. So you know that there are different classes of the electrolytes have some merits and demerits. One of the electrolyte, aqueous electrolyte, have a lot of merits. That it is environment friendly, very safe, cost effective, and highly conducting. Highly conducting in that sense. The only demerit is this, that its operating voltage range is very limited. So people are working in this safe electrolyte, how to enhance the operating voltage range, like in the water in salt system and all these. But still, it is under the investigation. So this works up to 1.2 volt only, even less than that. So this is the one limitation of the liquid, this aqueous electrolyte. And to overcome this problem, we have proceeded to the organic electrolyte, whose wide potential range we have 3 volt, but still they have a lot of problems like they are flammable, they are volatile, they are toxic. So these are also the safety concerns related with that. The third one is the ionic liquid. Ionic liquid have all kinds of merits, like they have a wider potential window, they are non-volatile, non-flammable, less toxic, and very highly conducting. The only problem with this ionic liquid is this, that the component ions of the ionic liquid, they themselves are mobile into any system. So actually, if you are focusing onto some target ions, batteries like lithium ion, sodium ion, and any other kind of battery, then those ions and along with these component ions of the ionic liquids, all are mobile, all are transporting. So the transport number is affecting those. So target ions transport number proportionally is very less. That's why you cannot think a very good material for the batteries. But still people are using because they have other merits. But for the supercapacitors, it is good because you need some ion to be accumulated at the interface, that's all. So this is a ionic liquid is a good material for as electrolyte, but into the supercapacitor technology, it is better, please. So good solution of these that to protect the material from the corrosion, from the various other aspects, these polymer-based electrolytes, which are further classified into three groups: solvent-free solid polymer electrolyte, gel polymer electrolyte, and porous polymer electrolyte. So solvent-free polymer electrolyte, its conductivity is quite low, the order of -5 and -6. It is useful for some other technology, but in battery and supercapacitor, it is not. In the gel polymer electrolyte, the conductivity is high. Many people are working on this area. And the last one, the porous polymer electrolyte, is technologically not very feasible everywhere. But those who are able to make it, it is a very good material, very accommodative material. So I'm going to talk about the porous polymer electrolyte today as an example study. But okay, so various types of solvents we use, like aqueous, organic, ionic liquid, plastic crystal is another story. So I'll not go to that, please. Okay, so I'm coming to the porous polymer electrolyte particularly. In this technology, what we do, we do that, we choose the suitable polymers and we create the porosity inside by some methods. So these are several methods, and one of the very important method is the phase inversion technique or the solvent non-solvent technique. So in that, what we do, that we take the polymer, dissolve in some suitable solvent, and then you put some non-solvent into that, and then try to evaporate the solvents together. The non-solvents creates porosity inside the polymer when you are drying it. So once porosity is created, like first time, Tarascan group has given this idea that if you are taking the PVDF HFP and two solvents they have chosen, in that DBP was extracted from there, and then it created the porosity like this, that you can see the surface morphology of the PVDF. It is porous. So in that, you can put any kind of liquid electrolyte and just soak it. But the only thing what I would like to mention, that a immediate question comes into mind, that if I'm talking about porous polymer electrolytes, then why not filter paper? Why not glassy fiber? What is the problem in those? The only thing is this, that since it is a well-chosen polymer, so what happen in that these kind of polymers, that their size of porosity is not bigger as it is in the commercial porous material. Secondly, when you are choosing any solvent, the liquid electrolyte, then the nearby area in the porosity, the boundaries, they get gelled to some extent. And so, in that way, the retentivity of the liquid electrolyte gets better, whereas it is chemically supported because of the jellification, and that's why a partial one. That's why retentivity is very high as compared to any commercial polymer. In that, in the commercial the porous material, these are only the physical absorption. So their evaporation is very fast. But in this kind of technology, it was first evolved by a well-known company, that was Belcore Technology. But nowadays, they have left it, and people were silent for a very long time. After that, it has been started once again. But it is not very popular, but it is a good technology. Please. So what we have done, this is the case study from my lab, that we have taken a polymer, particular polymer I have taken, that's name is polycaprolactone, that is PCL. Polycaprolactone is basically, people generally take a polymer like PVDF HFP or any other commercial polymer, but they are they are the not biodegradable. If you are using it in battery, and if battery is recycled or thrown, then these major component electrolyte is not biodegradable. So in this case, I have chosen the polymer which is biodegradable. So polycaprolactone PCL is a very famous biodegradable material. You throw it, it will be absorbed in the soil. Well, so I have taken it, and first time we have made it porous. Earlier it was used in several ways, but it is a porous material we have prepared, and so it is a very eco-friendly material. And at the same time, their glass transition temperature and their melting temperature is also very suitable. It is almost like polyethylene oxide. Yeah. So it has a solubility in most of the solvent except water. So water is a non-solvent in that case. It is also a good quality, that it has this hydrophobic material like PVDF HFP. So we have soaked it different ionic liquid and organic electrolytes to form porous polymer electrolytes, and used it into the batteries. Okay, please go ahead. Well, so you can see that these are the flexible materials. So polymer itself is a flexible, and then we have soaked it 1 NaClO4 into ECPC, then some ionic liquid, and then NaClO4 in, and this last two I have taken for the comparison with the PVDF HFP, which is the non-biodegradable. So the first two is the biodegradable material with PCL. Please go ahead. Well, this is the morphology of the material what we have found. The PVDF HFP, the downward, their porosity is not much created as compared to the PCL. It's a good porosity is created. And this is the morphology taken from the SEM. And you have seen that in the PCL, the bigger pores have the broader pores at the mouth, but inside the pores is another pores are also there, which is micropores. So this is the beauty of this material. Please go ahead. So this is the measurement of the porosity of any polymer material once you are creating. This is one of the method which is called the butanol uptake. Put it into the butanol, how much weight it is taking, and then from this formula you can find out what is the porosity in percentage. So we have found the porosity up to around 80% porosity in the material. And this is the electrolyte uptake, means how much liquid electrolyte it will have retentivity, how much liquid electrolyte it will take. So it is also close to 100% electrolyte uptake is there. Please. Please. Okay, so I have measured the ionic conductivity. Ionic conductivity is behaving like a molten gel polymer electrolyte-like behavior following this VTF equation, and it is a curved nature. Second is also the important material that you see that upper two is the potential window for the PVDF HFP, which is non-biodegradable, but PCL is a very important material, so that it is showing the potential window of the around 5 volt. So 5 volt is a very good potential window. And you know that if you have a cathode material, if you have anode material, their combination even more than 4 volt, you can go for the 4 volt class of the batteries you can use here. Okay, flexibility of this kind of material is this. You want to put the lithium liquid electrolyte, you can put it, sodium liquid electrolyte, you can put it, magnesium, whatever it is, zinc liquid electrolyte, you can put it once you have formed the porous material in that way. Please. Okay, next one I'm talking about the hard carbon. To make our device the carbon based, one side I have taken the activated carbon, other side for the hard carbon, and I have taken the raw material, a biomass, waste biomass, in the form of sugarcane bagasse. So from the sugarcane bagasse, we have prepared the hard carbon, which acts as a good anode material, and activated carbon from the same, which is working as good cathode material. So please go ahead. Well, so this is the some mechanism of the anode and how much is the capacity can be obtained theoretically. This is the one of the story. Well, go ahead, please. Actually, hard carbon anode from sugarcane bagasse we have prepared from this method, that we have taken this waste biomass, we have pyrolyzed it at and carbonized at 950 degrees centigrade, and after that we have prepared the electrode material directly. But if the same material, after carbonizing it, we are activating it by using some zinc chloride or any KOH and all these, it will behave as a hard carbon, the activated carbon, which will create more porosity and more surface area. Their surface area is not very large. Okay. Two types of carbon actually we have prepared hard carbon. One in which the raw material was soaked with ethanol, and other without soaking, and it was used the hydrothermal method. So soaking with ethanol, actually some of the lignin, which is the part of any biomass, it gets extracted. So rest is the cellulose and hemicellulose. They create another kind of hard carbon. If with lignin, they create the another kind of hard carbon. So we have just tested it. And by comparing, we have found that if you are ethanol soaked material, if you are taking, it always gives better material as a, so we use it in activated carbon also, we use it in hard carbon also. So better performance it gives. Please go ahead. Yeah. So BET surface area and porosity we have measured. The hard carbon directly what was found surface area 407. It is not good for the anode material. Hard carbon ethanol soap, it is giving 19 meter square per gram, it is good. The total pore volume we have calculated, average pore size we have calculated. From the average pore size, it is shown that several ions can be intercalated and deintercalated very easily. And so if you are talking about the sodium ion intercalation, deintercalation, it is a easy material. Okay. Actually, the sodium ion, lithium ion, they are all solvated. So you need a better accommodative interlayer spacing or voids for a node. Well, so we have prepared the 4 half cells of the sodium ion capacitors. We have ended here with the half cells because we are not touching the full cell using the activated carbon. It will take a lot of time. So I have limited time, so I'm completing it with this half cells only. So these half cells we have prepared from the activated carbon with for the comparison. I have taken liquid electrolyte also and porous polymer electrolyte also with the ethanol soak and with the harder carbon which is not used for ethanol soak. So it was made, and then we have tested it by taking these cyclic voltammetry, EIS and galvanostatic charge discharge, and then long-term cycling we have tested it. Please go ahead. This is the cyclic voltammetry. In that, you know, this is the cell 2 in which the porous polymer electrolyte and with the sodium one side as a reference electrode, and EHC, yeah, ethanol soaked hard carbon, is other side, and we have tested it in the cyclic voltammetry. And this cyclic voltammeter has been divided into 3 parts, and 3 peaks you can see, that is 0.8 volt, 0.5 volt. 0.8 volt peak is the hydrogen oxygen reduction peak. 0.5 volt is related to electrolyte decomposition, and the most important peak is at 0.1 volt, in which the cathodic and anodic peaks both are observed equally, and it is highly reversible, and they are actually related to the sodium ion extraction and insertion, and so it is a good cathode anode material. So cell 2 has given a better performance with the ethanol soap material. Please go ahead. Okay, this is the galvanostatic charge discharge test. In that, you can see there are 2 distinct regions for any charge discharge pattern what we have. This is the charge discharge pattern with the different current density, and this last one is the charge discharge current for the different cycles. And we have seen that for the first discharge cycle, we have got a very high capacity, but you know that never rely on the first discharge cycle. We go ahead, so its capacity is reduced to 220, which is still very high. Well, so 2 distinct regions are there, from 2 volt to 0.1 volt and 0.1 volt to 0.0 volt. 0.1 to 0.0 volt is related to the sodium ion extraction, de-extraction in the graphitic layer of the carbon material, and 2 volt to 1, it is related to the adsorption desorption of the sodium ion. The 2 mechanisms are involved. Adsorption desorption gives a very fast response in decreasing and increasing the charge discharge, where stable performance is because of in the lower voltage region. So capacity is very high and substantially high. Please go ahead. Yes, this is the current rates and long cycling. You can see that the cell 2, what is at different currents, it has been tested. You can see that if you are increasing the current, the capacity is decreasing. But as soon as you are coming back to the previous, the lower value of the current, it regains. So it means that battery is not permanently deteriorating. Actually, this is the current. If you are increasing the current, the performance will be lower, capacity will also be lower. Well, so best performance is from the cell 2 with EHC and sodium, and so I have tested it for different cycles. This has worked for up to 300 cycles. So this indicates that hard carbon by ethanol soaking powder and porous polymer electrolyte shows the best performance, and hard carbon is suitable for the sodium as sodium ion capacitors. We have tested it. Please go ahead. Well, so what we have done the what is this is called post-mortem study. Means you take the some measurements like FeSM before the cathode material or anode material. Here I have taken the anode material EHC before cycling it into the battery and after cycling it after certain cycle. You can see in the 10 micron expansion that the flake-like structure is obtained initially into the carbon material, but after the 300 cycling, these are broken into the due to and in the form some holes are created, and so these holes are because of the continuous shuttling of the electrolyte ions through the pores. So pores are created during the charge discharge. So this is the post-mortem study, and this is the before cycling, this is after cycling. This measurement gives you a direct imaging and evidence of the charging, discharging, and change into the feature of the electrolyte, electrode material. Okay, go ahead, please. So in this way, I would like to summarize it that sodium ion storage via sodium ion capacitor has been excellent potential, and it is good alternative to lithium ion technology. Hard carbon, which is produced from very local resources like sugarcane bagasse, it is also called different waste biomasses you have that will give you a better and stable result even in NIBs, even in NICs. Well, so pre-treatment of this sugarcane bagasse we have tested. In other works also we have tested. This is a very good approach to increase the efficiency of the anode material or even activated carbon. Then porous PCL film, which is soaked with this sodium chloride ECPC, we have found that it is a very suitable electrolyte for the high ionic conductivity. And then you can make the flexible device. Instead of using the liquid electrolyte, you can use this kind of device. So EHC anode shows high discharge capacity. The stable value we have found 212 milliampere per gram as compared to the without methanol, it is 120. So almost double we have found the capacity. So this is the story of the biodegradable material as electrolyte. We have tested it. If you are throwing your material, your battery, even in environment, it will not harm much. It will not, it because of its biodegradability. So with this, I am closing this. Thank you very much. Yeah, I would like to acknowledge my institute, my students. My university is the institution of eminence, and so we get some funding from that there. So I would like to acknowledge for financial support. Once, thanks. स्लाइड बढ़ाइए ये जरूरी हाँ या थैंक यू
Thank you, sir, for such an informative talk. Thanks for sharing your crucial work, contributing in the quest of a cost-effective and less toxic alternative to lithium-ion technology and the greater cause of sustainability.
Thank you.
Any questions?
I'm here for 2 days. So any question, even if it generated even in 1 day, 2 day time, I'm here. Okay.
Hello. Thanks a lot, sir, for such a lovely talk. Sir, it is a new question, sir. I don't think, since I'm not from capacitors and material science, so you state that ethanol is used in order to remove lignin from that. What about butanol? Somewhere you are dipping that in a butanol solution, I guess.
Ethanol is able to dissolve the lignin component of any lignocellulosic material. So I have chosen the ethanol in this case. So the purpose was just to remove the lignin and see, because in other technology, some work, we have seen that if lignin is not there, then the expanded layered structure into the carbon, you can form it. And so if lignin is present, so this is very partial, and if it is not present, then fully expanded anode material, expanded layered structure, you can find because of this absence of the lignin. So that's why it was used. Ethanol is the solvent of the lignin. That's why yeah. Okay, I think there is no other question.
Yeah,
So
I think there's,
yeah.
no. Okay, so we'll start our next talk after 5 minutes.
and battery by Professor Hashmi, right? So when we do the research in physics, as I mentioned in my keynote address as well, so two type of platforms are there. One is experimental and second is theoretical. And with the advancement of technology, both aspects are very important now. And I will say one cannot go without the other. If you have to reach your range, okay, you have to increase your readership. Okay, so it should be a combination of theory as well as experiment. Okay, so in my talk, I will try to give you the introduction about a powerful tool from theoretical side that is called density functional theory. Okay, in the layman language, I will try to do so that you can at least understand and try to do something by your own, because in these days on internet you can find some basic knowledge about any computational tool based upon density functional theory and can start learning by yourself. I generally give to my MSc intern a new type of the project. Okay, you learn this particular DFT software or code and try to do some at the first stage the known problem and then come to the unknown problem. For example, okay, so if you are beginner in DFT, try to have the or try to plot the band structure of silicon. Try to find the band gap of silicon. What is it? How much is the band gap of silicon? It's 1.1 electron volts. So are you able to do it from computational point of view? So if you can do it by your own, you will see that, okay, so I have just done whatever I can do from experiment. Okay, you will design a particular crystal or you will synthesize a particular crystal, go with the UV visible spectroscopy with the help of top plot, you will estimate the band gap of the same, right? So this particular exercise you can do from the ground state calculation only using the density functional theory by just accessing the density of state, that is DOS or band structure. You can predict what is the band gap. Not only the band gap, you can tell whether it is a direct band gap or indirect band gap, right? So this is the first task which we can do if we are starting our theoretical research. And then everyone know that iron is a magnetic material, fine. And we know the magnetic moment of iron is 2.2 Bohr magneton. So from theoretical point of view, you can also get, after doing your ground state properties, ground state calculation, you can have on your screen by just giving the command what is the total magnetic moment on the iron. So if you're getting 2.2 Bohr magneton, you will see again, you will also feel some enjoyment that you have done something good. Okay, sitting on the computer, you are just designing the experiment, right? And I will try to deliver in the layman language, and you should understand that what the message I want to give. So it will not be a hi-fi research, okay, though I will cover some aspect of my research as well, but just the glimpse, because if you can understand the basic one and do by your own, from learning from the YouTube video of any particular DFT code, definitely you can start. And then you can jump to the HPC server. You can ask your supervisor, you can ask your teacher you the access of HPC server of any particular university, and then you can log in for the disordered material also. For example, just I have talked about the ordered material like BCC iron, you can go for the magnetic moment, and the silicon, you can find out the band structure. So it is, the band gap is 1.1 electron volt, and it is the indirect band gap semiconductor. Okay. Okay, so I think everything is ready and I can start my talk. Fine. Okay, so again, thanks the organizers. So it's a wonderful arrangement by the organizers, and we are standing here proudly that we can try to give some knowledge about the recent development in applied physics, and the topic which I will cover is condensed matter theory or theoretical condensed matter physics, and it is based upon density functional theory. Right. So topic I have taken is density functional theory for modeling of advanced material. Right. And next slide, please. So I am coming from Jawaharlal Nehru University. So everyone, I think, aware of this particular university. So we are research university mainly. So our main focus is research and teaching also, but we have only PG classes in School of Physical Sciences. That is only MSc and PhD. Okay. Though we teach BTech classes also for physics, but that is running in some different school. Right, so this is our convention center. So if you are coming for any conference in JNU, so you will definitely go in this particular convention center. And next slide, please. So I will take my talk in this direction, including the topic like history. So from where we have started, the foundation of density function theory, background, fundamental of DFT code. There are many DFT code or software you can say. So out of these, I will try to give you some glimpse about Win2K and VAS. So these are the two powerful computational code for DFT. Just the glimpse. What is the input? What is the output? Okay. What are the input file? What are the output file? Advanced DFT functional I will try to cover, and finally I will show some of the result that how we are helping the experimentalist or how we are trying to predict the new materials from computational point of view using the HPC server, not on the simple computer like these laptops are there. Next slide, please. Okay, it is 1920 when Thomas Fermi gave the model. Then he tried to imagine the density as a fundamental variable for predicting the wave functions. And in 1928, it was Hetry method. Okay, so he tried to give the potential. Okay, so when we have to give the ground state property of any particular material, so we have to suppose solve the Schrodinger wave equation. I will say as a fundamental equation, it is H psi is equal to E psi. So H is a combination of two operator. One is kinetic energy operator, second is potential energy operator. Okay. So kinetic energy, no problem. But potential is a big problem. Potential energy, how we write the potential energy or potential energy operator. Okay. So in this, whenever the electron are many in number, okay, so they are not independent. Okay, it's not the free electron. It is the one electron has to move in the cloud of other electrons. So this means exchange as well as correlation. Both effect comes into the picture. So Hetry method has given a potential, but in this, no exchange term was there. Then Hetry-Fock method, so he included the exchange term. Okay, two electron can exchange their position, and accordingly he adjusted the potential. Right, so but still correlation term was not there. Then in 1964, Hohenberg and Cohen have given us a paper in which he has shown the existence of exact density functional theory, in which both exchange as well as correlation terms were involved. And so from this was the initial point of density functional theory. Right, so okay, so we are having a particular equation and we try to solve it. Okay, so there are two methods to solve a particular equation. One, we solve it by hand on the paper, that is called the analytical way. And second one is the computational way, in which we try to make it in an iteration manner. Okay, so then in 1965, Cohen and Shaham gave us this scheme, which is nothing but a computational based scheme. You have no need to solve now the basic equation of the density function theory, that is called Cohen-Shaham equation. It is just derived, you can say, from Schrodinger wave equation. H psi is equal to E psi. So with the help of the computational scheme, so we will be able to solve that one using the iterative method. Right, so this means DFT now has come from paper to computer. Okay, so and you can just see within the span of 5 years, 1970 and then early 80. So DFT becomes so much powerful, and people started to work on the density functional theory and try to do the material modeling. And those days, it was not the easy thing, you know. So if you talk to your teacher, how did you work on the computer on those days? It was the time of floppy, right? It was before that, it was the computational cards. So punching machines were there, and then floppy. What was the size of the floppy? Do you know? It is 1.444 MB, and today we are talking about TB. So I have witnessed when I have started my research. So I have just gone with the floppies. Okay, so we try to take the data in the floppy and then keep it preserved. Then CD came, then DVD came. Okay, so now everything is in the pen drive. Okay, small pen drive is there, and many GB you can cover up. Okay, otherwise from a small computer, we have to take the data again and again in the floppy or CD or DVD, and then we have to run the other calculation. And the life was not so much easy for the previous generation, means my supervisor or his time, right? So they have to wait on the computational facility wherever it is developed in any university. So they have to wait for their turn to run their calculation, right? So that wait may be very long as well, right? Back slide, please. Okay. So you see here Walter Cohen, who were involved in both the theoretical description as well as in computational description, was given a Nobel Prize in chemistry in 1998 for the development of density functional theory. Right? Next slide. Now, as I said, it is nothing but the question of the potential. So this is the fundamental Hamiltonian. See, I am showing you here the first two terms, these are related with the kinetic energy. And the third, fourth, and fifth term, these are related with the potential energy. Okay, so first one. So this is I and A. So A and B run over M nuclei. You can say that. So and Ij is for the N electrons of whatever we are showing here. Okay, so the very first approximation, whenever we go with the quantum mechanics, it is nothing but the Bohr-Oppenheimer approximation, which try to say that the position of nuclei are same, fixed. Okay, so suppose we are having two atoms. So for the two atoms, their nuclei position of the nuclei are same. So this means no kinetic energy term is involved for the motion of the nucleus. It is only the electron which can move. So it has reduced one of the term related to kinetic energy of the nucleus, right? So wave function was depending only upon the nuclear position, but not on their velocity. You can say that. So means nucleus cannot move. And definitely nucleus motion is so much slower as compared to electronic motion. So nuclei are fixed, so we can neglect the kinetic energy of the nuclei. So we are having now the Hamiltonian related with the electrons, and you can get H psi is equal to E psi for the electron in this way. So electronic and nuclear degree of freedom were decoupled with the help of this particular approximation. But so even it is involved. So we have not said anything about the exchange and the correlation. Next slide, please. Okay, so this is the Hetry method. So whatever I have written in the very first or second slide, what was involved in Hetry method, Hetry-Fock method. So the same thing is there. So see here, Hetry method. So it is a total wave function. It is nothing but the product of single electron wave function. Okay, suppose n electrons are there, so it is nothing but the product of individual wave function of the electron. And so in this, the exchange and correlation interaction between the electron were neglected. Okay, so it is not there. Then you can say that the Hetry-Fock method, the wave function was in the form of the Slater determinant. So in this, you see one term is there, that is Vx. So it was not there in the previous one. So Vx means exchange interaction was involved, right? So still it is correlation was not involved. So this means we were having a large deviation from the experiment one. For example, suppose from the experiment, silicon band structure is 1.1 electron volt, and from the theory, it may be very less. For example, it may be 0.4 or 0.5. So it is not acceptable. We have developed this theory. We try to develop a theory in such a way that it should give you the same result, whatever we expect from the experiment. Okay, so it was not there. So this means there is some lacuna, right? So that lacuna is nothing but the correlation term. Next, right? Okay, so the problem of solving, and definitely when we say that the wave function is a combination of or multiplication of n different wave function depending upon the n electron. So it is a huge wave function. Okay, so means many body problem is there. So if we can try to check, or we can try to change the many body problem into one body problem, then our job is completed, or you can say that easy. So problem of Schrodinger wave equation of n particle system can be resolved with the help of density function theory. And you can say that in many body wave functions, psi is a central quantity, Hetry and Hetry-Fock method. So this has been tried to approximate it, but still it is a n depending upon n electron. Okay, so one electron is having 3 degrees of freedom. So this means psi is containing 3n variable. Okay, so this means it is huge wave function. So is it possible to replace it with a simpler quantity, right? So that we have to think, and so this approach is very complex, you can say that, and numerically very much demanding. And new approach to many body interacting electron problem is called density function theory. Next. So this is the importance of density function theory. So you can say that a solid is described by the wave function of all the atoms and the solution of 10 to the power 23 electrons, and combining these one is almost practically impossible. Why I've written this 10 to the power 23? Because we say that unit volume of the crystal contain Avogadro number of electrons, or Avogadro number of atoms, you can say that. Suppose I say one atom is containing 1 electron, then it is 6.023 into 10 to the power 23 electrons. So accordingly, these much number of wave function will be involved, and the combination of all these will give you the final wave function. So this is practically impossible from computational point of view. So what we try to do, we try to describe the single electron in the mean field of atoms and other electrons. And the basic idea is that we try to take the help of functional, right? When I talk about the functional, so I'm not saying that it is a function of function. Okay, functional is not the function of function. Function of function is composite function, like you have talked about FOG or GOF in the previous classes. But here functional is something different. Okay, when I say E is a functional of rho, right? So this means rho will not come in the final expression of energy, right? Okay, so system depends only on the 3 spatial coordinate, because if we say that I am having an isotropic material, so its density can vary only in the 3 directions. So density can have 3 variables only. So this means with the help of writing the wave function in terms of the functional, or writing the operators in terms of the functional, so you have reduced the degree of freedom from 3n to 3 only. Right? And knowledge of density is sufficient for the complete description of all the ground state properties of any atom or molecule. Next. So see here, so Hornberg and Cohen have given 2 theorems. So based upon these 2 theorems, so we have developed each and every aspect of density functional theory. The external potential VR is a unique functional of electron density. Okay, so means potential we can drive from the density, and total ground state energy of the many electron system is also a unique functional of density. That is E is equal depending upon E. So square bracket means functional. Whenever we write a small bracket, so it is a function. Square bracket is functional. Next. And the second theorem is that how to find the ground state energy. So the true ground state energy, or true ground state charge density, is that which minimize the total energy. So what you will try to do, you will take the ground state energy and try to take the first derivative of that, put it equal to 0, and try to find the what is the value of E. Take the second derivative, check whether you're getting the minimum or not, depending upon the sign in the second derivative. So if it is so, so this means you have achieved the ground state energy. using the minimization of the ground state. And in this way, the Hornberg-Kohn theorem constitute the basic of the density, but do not offer any way of computing. So that's what I'm saying. Still, we are on the analytical way. We are able to solve it, but from the pen and paper. Okay, next slide. So then the Cohen-Sham approach or Cohen-Sham method comes into existence. See, so what we have done. I'm showing you the two pictures. For one is for the 3n variable, second is only for the 3 spatial variable. What is the difference between these two? So both can give you the similar type of the result. In first picture, we are saying or we are showing the some electrons. So these are interacting with each other. Okay, for example, you focus on first electron, it is accelerator, brake and clutch. How much fuel is there? What are the traffic rule? You can drive the car. Okay, in the same way, by just know what is your input file, how to make it, and then what is the command to run, you can get your output file. No need to go in the deep how the code is written, right? So this means, and the spending time in the driving is depends upon variety of the road condition. So I'm correlating it with the density function theory calculation. So you can say here, so density function theory calculation depends upon what type of system you are having, whether it is ordered or disordered. It is containing less number of atom, it is containing many number of atom, right? So based upon that, you may have difficulty or you may have the easiness to run the calculation. Okay, so means time is involved. Without knowing many technical detail that how this fuel injector, radiator, brake, all are working, you can cross the town. Okay, in the same way, without knowing the internal mechanism of density functional theory, how the exchange correlation potential are working, so you will be able to find the ground state energy. You will be able to find the band gap. You will be able to find the magnetic moment. But last point is the important point. Building a new car, you need the expertise, right? Okay, means new method if you have to develop in the density function, so you have to dig inside the code. Okay, in that case, you need the expertise. Next slide. So see here, so it is you. So who is expert or maybe beginner or maybe intermediate one, sitting on your computer table, running a DFT code. Okay, so for this calculation is running on the HPC server, so it may be a very small computer, so no need to worry, right? And you can cover all these things. See, many properties I have written and many such areas I have written here. Nanomaterial, transport property, optoelectronics, nonlinear optics, magnetism, band structure, magnetic property, defect engineering. When I said defect engineering, it can be substitutional, vacancy defect, dislocation, absorption, doping, interstitial. All you can cover with the help of density function theories. Now your crystal will be disordered crystal. Next slide. So see here, so these are the some DFT codes, right? So depending upon what type of system we are having, we have to choose a different code. For example, it is local orbital basis code. So it can be Quest, Siesta, ATK, Crystal, Imperio, and so on. All electron code. So it can be ELK, exciting, Fluor, RSPT, and Win2K, right? So I have started my research from Win2K. So I will try to cover Win2K. Next, so when I said it is all electrons, so this means potential we will take for all electron differently, right? So we are having 4 type of electron. What are those? S electron, P electron, D electron, and F electron. Next slide. So we can have some computationally efficient code which are based upon the plane wave and related methods. So that is called VAS, CASTEP, CMPD, ab initio, and list is so long. So you can just cover up these ones. Next slide. And the molecular code, when I talk about this, NWCAM, Octopus, DMOL3, Jaguar, Gammas, NRMOL. So all these chemistry people are habitual to do these coding. Next slide. So see here, I'm giving you the glimpse of 2 codes, maybe in 2 or 3 minutes. So first one is Win2K. So it is the augmented plane wave plus local orbital program for calculating the property of the solid, right? So this is the code developed by the Austria group under the leadership of Peter Blaha and K. Schwarz. Next. So what we do in this, so it is based upon full potential linearized augmented plane wave method, right? So we choose our unit cell in 2 portions, 1 and 2. In the 1, we are having the actual atom, and then the second, we are having the interstitial region, means no atom is there. Okay, so for both, we choose the different type of the functions. For example, whenever we are having the first region in which atom is there, so we take the augmented waves. So that is the A and U plus B and U dot. Okay, so this means we are covering the augmentation of the wave function here. But in case of interstitial region, we take only the plane wave. You know that in the interstitial region, if any electrons come, so it will behave as a free electron. So that's why plane wave solution is there. Next slide. So this is a program in which you can just see on your computer graphical user interface that is called GUI. And there are many Fortran program, so which are linked by the C script. So what you have to make, so you have to just open your terminal window and just make a directory. So for example, iron you have to work. Make a directory mkdir iron fe and then initialize the calculation. Okay, so for example, I'm showing in journal. So make a directory case. Try to make a master input file that is called case.struct and then initialize the calculation init underscore lapw, right? So it will set up all the input variable for you and then run the final calculation, run underscore lapw. So it will give you the self-consistent result like I have shown you the iterative method. Okay, so input, output, and SCF files are designated by the ending of the corresponding program. For example, if it is an output file, so output 1, output 2, and so on, it will be there. So if it is an input file, so then it will be like dot in1, in2, inso, and so on. And the same way, if it is self-consistence file, so it will be SCF0, SCF1, SCF2, and so on. So depending upon how many iterations have been run, so correspondingly, we will have this different type of SCF file. So all the input will be generated through the W2 web that is called the graphical user interface. Next slide. So see here, that's what you have to do. Just like what I said, that learn how to drive the car. See here, so this is what you need. For example, I'm showing you the TIC, right? So TIC is a material for this. What information you need? And you can just run the calculation. You must know what is the lattice parameter for TIC, and then you will fill on the ABC, right? ABC is there, alpha, beta, gamma. You will write the angle for this, and at what position TI and C are present. You will fill this position. You will save the calculation. In this way, your master input file has been generated. And then on the left, you have seen the initialized calculation. Okay, or on the terminal window, you can just write init underscore lapw, and all the input file will be generated in that case. And after that, you have to run underscore lapw, that is the command, and you will get the desired ground state energy. Next slide. Okay, so this is the glimpse, and then the rest you can take on the internet. And the second one, that is the Vienna ab initio simulation package. WASP is there. It is more famous because it used the pseudo potential instead of the actual potential. It used the pseudo potential. Next slide. It is also developed by the Austria group, but different group. See here. So here I want to show the importance of the pseudo potential. On the right hand side, I am showing you two graphs. One is the dotted graph, and second is the solid graph. Okay, and there is a second vertical line which is mentioned the critical radius. So on the right hand side of the critical radius, we are having all the electron which are present in the valence shell or in the second cell to the valence, or semi-core electron, you can say second last cell or last cell. And whatever the scenario at the Fermi level, it is decided by the valence electron, and maximum you can say semi-core electron. And on the left hand side of the critical radius, it is nothing but the core electron. Okay, for example, when I say core electron, so this means the first cell, second cell, third cell, fourth cell. If suppose one particular atom is there, the fourth cell will be the valence electron, third cell will be the semi-core electron, and rest you can take as the core electron. So for the band formation, you need only the information about the valence electron, maximum semi-core electron. And see, so dotted curve showing you these the actual potential and actual wave function, and the solid one showing you the pseudo potential and pseudo wave function. See, after the critical radius, both are same. Graph of both are matching. So it hardly matter whether we are using the actual potential or pseudo potential if we have to focus on the band formation, right? Or we have to focus on any particular calculation which is decided by the valence electron or semi-core electron. But what is the benefit? Instead of this, the actual potential, if we use the pseudo potential, we will use less time in the calculation as compared to the actual potential. Fine. So it is better to use the pseudo potential. And the method for this one is projector augmented wave method. It transforms the rapidly oscillating wave function into the smooth wave function, which are more computationally efficient. That is the information I want to give. So it is better to have the pseudo potential instead of having the actual potential. So VASP can be employed in any first principle calculation for all the cases. Next slide, please. Like I have shown you TIC in that case, in case of Win2K. So you have to fill some information like ABC and alpha, beta, gamma, where TI and C are present. In the same way, these are the 4 input file for the VASP, right? And 4 input file of the VASP is in-car, post-car, port-car, and key point. So when I say in-car, so in-car is a short word. It is nothing but input card. Input card means we need 4 cards to play the game, right? So in first one, that is the in-car, we give the information about the input variable. For example, we specify the parameter that define the calculation, global breakdown, energy cutoff, smearing factor, ionic and the global, ionic and the geometric relaxation parameter that we give in the in-car file. Second one is postcard. Like you have designed the TIC file, that is tic.struct in case of Win2K. This is a similar type of the file that is called postcard. So suppose many of the experimenters know that if they have to publish an article, they will go with the Rietveld analysis, Rietveld and refinement, and then they try to produce the SIF file, crystal information file. So that crystal information file can be easily converted into postcard, and the theoretician can run the calculation based upon that file. Okay, so that is the same file, postcard. So it specifies the periodic simulation cell information regarding the geometry of the system, means what is ABC, what is alpha, beta, gamma, what is the position of each and every atom. Then the port car. So like in the first case, in the case of Win2K, so we have to design the potential by our own, but here the pseudo potential are fixed. For each and every atom, pseudo potential are fixed. For example, we have to run the calculation for TIC. What we will do, so we will take from the repository the potential for TI and C, and we will club it in one particular file and give it a name as port car. So port car is the potential card. Second one, that is post car, is position card, and the final one, that is key points. So you have to define the key mesh. Okay, and then with these 4, so your calculation are ready, and then you have to just run VASP_std, and you will get the desired information about all the ground state properties in case of VASP. Next slide. Next. So these are the output file for the VASP, that is count car, OZ car, out car, and charge car. So first one contain the position of the system after the calculation has been completed. For example, so you have done some disorder, and you have taken your post card, that is positional card. Okay, so after the relaxation, what will happen to post cards? That is contained in this count card. So count card is nothing but the revised version of post card. Okay, so for your final calculation, you will designate this count car as the post car. In the same way, so how many electronic step and ionic step has been done? So it is information is given in OZ car, and in the same way, running the output, including the input data file, that is contained in out car, and charge density information, it is written in CHG car. Next slide. Okay, so this is the glimpse of 2 software which you can just look at the internet. Now, it is very important to have the information about the visualization software as well. So these are some of the visualization software in which you can visualize your crystal and do the manipulation in the crystal, do the suppose doping disorder, or just the making the crystal, making the unit cell large. You can create the monolayers, you can create the quantum dots using all these visualization software. So XCrystal is there, Vesta is there, VMD is there, Obito is there, Crystal Maker is there, P4 VASP is there. So very first 2, that is the XCrystal and Vesta are much more famous in this case, and both are free as well. Next slide. So see here, I'm giving the information that how Vesta is helping us. So I'm giving you the glimpse of heterostructure, that how you can design the heterostructure. Okay, so heterostructure is nothing but the combination of two 2D materials, and the final heterostructure will contain the property of both the material within the one material. So see here, so I have taken the graphene and hematine. So we can combine graphene and hematine in terms of a heterostructure. That is nothing but van der Waals heterostructure. Okay, so what we have to do, so we have to take the supercell of individual layer, for example, graphene and hematine, and selection is done in such a way that there is the minimum lattice mismatch, right? And after that, after selecting the particular supercell for graphene and supercell of hematine, you can relax the calculation, and after the convergence test, you can check how much vacuum thickness you needed. Okay, so in this way, you can design the heterostructure. Next slide. So what is the motivation of doing all these things? So we are going from wet lab to the dry lab. Wet lab means experimental lab. Dry lab means the computational simulation, right? So HPC users, you can do fine. So I have told you that you can go for the any remote servers and do your complex calculation. And you can reduce the experimental trial. For example, you have to design a particular alloy based upon the composition of X and Y, and you don't know how much X is needed, how much Y is needed for an optimum composition of X and Y. Okay, so you, from experimental point of view, suppose you do 50 trials, and then you finally come to a conclusion that, okay, the one particular one is giving me the exact amount of the information. Okay, so this means out of 50 trials, 49 experimental trial are waste for you. What can be alternative? So do the 50 calculation on the computers and try to get the result, find out the optimum configuration which is needed, and do the experiment only on one configuration, right? So in this way, you have reduced the cost of experiments of 49 trials. So it means you have done only one trial and you have got the desired result as well. Okay, so this means we can limit the wet lab use. So all trial can be performed on the computers using simulation and select the desired configuration and go for the experiment. So in this way, we can help the experimentalists. Next slide. Okay, so DFT in material science, so simulation of bulk and nano materials, ground state property you can cover, magnetic property, optical and non-linear optical properties, thermal properties, vibrational properties, elastic properties, many properties are there. So I have mentioned some of these. Next slide. Don't think that density functional theory is having the use in physics and chemistry or engineering research. We find the use in biological system as well, because biological systems, we have the internal mechanism in such a way that these are also molecule or polymer, you can say. For example, I'm giving the one particular case in which density function theory is useful for complex biological system. See here, before enzyme binds substrate. So try to find the energy, ground state energy, that is the case of the natural state, and then enzyme is released by the substrate. Then try to find the energy. So is it same or different? If it is different, then you can say that, okay, enzyme has left the substrate. So in this way, with the help of density functional theory, we can study the protein system. Okay, and everyone know that in chemistry, the Nobel Prize has been given on the protein synthesis, not from experiment side, it is from theoretical side. John Jumper is the one of the Nobel Prize winners, and it is not very much. It is, I think he is in 30 or 40 years. Okay, not too much old, right? So what are the challenges in this particular case? Many interaction happening simultaneously in the biological system, so we can just focus on one. But anyhow, so we can check some success which can be modeled together. Next slide, please. So now for the next 2-3 minutes, I will just try to show the results, how we have tried to take the help of density functional theory and help the experimental, or how to get the new result. For example, I am taking the three particular cases: 2D material and heterostructure. We can try to predict, and the prediction of magnetic alloy. And suppose I am taking the ETL, that is electron transport layer of hybrid halide perovskite solar cell. Okay, so what is the benefit of all these things? So for the first one, these are the nanomaterials for the magnetic applications. Second one, what we can check which magnetic phase is there for a particular alloy composition, that can be checked. And the alternative for the silicon solar cell we can find in the perovskite solar cell with the enhanced efficiency. Next slide, please. So see here, so this is a hematine. It is experimentally synthesized, maybe I think 18 or 19, and we try to give the Curie temperature for this. Okay, so hematine was the 2D material, which is nothing but like graphene is there. Graphene has been derived from graphite with the help of scostrate exfoliation, right? In the same way, the hematine can also be derived from the hematite, which is nothing but iron ore, Fe2O3, and it is again a monolayer, right? And in the monolayer, so what we can say that hematine is the most far-reaching ultra-thin magnetic indirect bandgap semiconductor. I'm saying indirect magnetic semiconductor. So this means in the one spin it is having the different bandgap, in the other spin it is having a different bandgap. Okay, so we have obtained the TC, and we can also find the magnetocrystalline anisotropy and magnetic moment for these cases, and we have just produced the strain effect also. So with the help of strain effect, how it is affecting the magnetic moment for all the tensile as well as compressive strain, we have just checked in this particular case. Next slide. So what we can see which configuration, magnetic configuration is stable. So based upon the two different type of the sublattice of Fe, so we can design 5 configuration and see here, so which one is the maximum negative. So you can say that one is a stable one. So A5 is coming out to be stable, in which we are having two different sublattices, that is Fe1 and Fe2. Fe1 is having different environment, Fe2 is having different environment. One is containing three carbon atom as a neighbor, and second is containing 6 carbon atoms. See in the figure. Next slide, please. So this is just a glimpse that I'm showing you. So second is heterostructure. So we have tried to design the heterostructure of graphene and HMOS2. And what we can do, but we can absorb the CR in this, and we can change semiconductor into the metal. So this means we can induce this significant magnetic moment in both the stable configuration. We will have 2 stable configuration in this particular CR adsorption, and the resultant adsorbed heterostructure can be a efficient candidate for these spintonic or nanomagnetic devices, right? And we can do the density of state analysis, partial density of state analysis, and we can just check which states are responsible for having this type of the effect. Next slide. So see here, so depending upon where we are adsorbing the CR atom, we can have 4 different configuration, that is G hollow, S hollow, G top, S top. So when we talk about hollow of G means we are adsorbing the CR atom on the graphene layer, and S means we are adsorbing the CR atom on the MOS2 layer, right? And hollow and top, so it is directly on the top of the carbon atom, okay, or it is it is in the center of the hexagon. So it is defining the top as well as hollow configuration. We can have the band structure, information of the band structure, and we can predict the result in this way. Next slide. So see here, so this is the third case in which we try to see which one is the stable magnetic configuration for the intermediate alloys. So see here, so this is the compound. 4 compound one experimentalist group has designed. So I am just saying that, okay, it is U2, Ni21 and B6, and in the same way it is Ni2, NB2, Ni21, B6, and the second way NB3, Ni20 and B6, NB2, Ni20 and B6. So means four different alloys the experimentalist group has designed. So out of these 4, only 2 were coming out to be stable and 2 were coming out to be unstable. So with the help of density function theory, we have tried to show using formation energy that whatever the experimentalists are getting, so same result we are getting. So this is not the complete picture. So they have seen that in the intermediate stage, that is the compound which is Nb2.5, Ni20.5, B6, it was showing the polyparamagnetism and it is having a tiny magnetic moment. So now, so if I say, okay, so one Nb2 and Nb3. Out of Nb2 and Nb3, one is forming and one is not forming. And the intermediate one is forming and showing us the different type of the magnetic behavior. So what is the reason for that? Okay, so it was having a tiny magnetic moment of 0.6 Bohr magneton, right? So that was the experimentally recognized. So we try to give the answer from the density functional theory point of view. So this is a calculation based upon the Win2K because it is a bulk material. And we did the fixed spin moment calculation. We have fixed the magnetic moment by 0.6 Bohr magneton and try to check which states are responsible. And based upon the partial density of states, we have identified those states and given the answer to the experimentalist and then published this paper. Next slide. So this is the last one. So see here, this is hybrid perovskite solar cell, and it is containing mainly 3 different layers. One is the absorbing layer, second is electron transport layer, and hole transport layer. And this is the complete solar cell which experimentalists design. Okay, so as I mentioned, from theory point of view, you can go with the material simulation as well as device simulation. This complete device can be simulated and you can get the efficiency using the numerical simulation. But from the density functional theory, so you can focus on a particular layer and try to see what type of physical property that a particular layer is having. So for this, we have tried to check the ETL. Okay, so the famous ETL was TiO2, right? But TiO2 is a different type of this structure and the perovskite is having a different type of this structure. So means lattice mismatch is there. So based upon that, we have tried to check, is it possible to have the ETL also from the perovskite type of structure? So based upon that, next slide. So we have taken the BSNO3 and in that also we try to adopt the LA. So what we have seen, this is the experimental dielectric function and the dotted one is experimental result and other one is our theoretical result. So what we have seen that, okay, so we have got the similar type of the result from the experiment. And not only that, we have just checked, so what should be the property of electron transport layer? So it should have very less absorption and very less reflectivity. So whatever is the light, so light is coming from the bottom. So first ETL come and then the absorbing layer. So means whatever the light is coming, it should be directly transformed or transmitted to the absorbing layer. So means there should be no reflection, there should be no absorption. So that's what we have predicted, that absorption as well as reflectivity is very less. And with the help of LA doping, so some of the absorption is reduced and reflectivity is also reduced. Next slide, please. So in this way, so we can also help the experimentalist to design a particular layer of the solar cell as well. Next. So this is the conclusion. So density functional theory is the one particular computational tool in which we can take the help of electron density to give the information about the ground state property of the crystals. And by focusing on the electron density, it is possible to draw the information about the one electron based Schrodinger wave equation that is called Kohn-Sham equation. And these computational tools based on the density functional theory are widely accepted these days and calculate the magnetic, electronic and structural properties of any type of the system, whether it is molecule, material, disorder or ordered, and many computational tools are there. Okay, so DFT gives you a variety of the molecular properties like mentioned here. So knowledge of correct density functional theory is sufficient to give you the desired effective result. And the important point, the advancement in the HPC server, HPC technology gives you the freedom that you can simulate the material at your home and you can focus on the disorder material. With these words, I end my talks. So thanks for your kind attention. So these are my students who have helped in doing all the work what I have done. So I'm having the guidance from Professor Bruce Harmon, Professor B.L. Oja and Tashi Notial from AIMS Lab, Udaipur University and IIT Roorkee respectively. Thank you.
Thank you, sir, for such an insightful talk. Thank you for enlightening us as to how we can expand our research skill set without heavily depending on a fully functional wet lab and expensive raw materials. We are now open for questions. Any questions?
Maybe 11 question only. Yes. Go with first.
First of all, thank you so much. The talk was very interesting and engaging. My first question is, as you said that refinement is the input in DFT. So dealing with biomaterials in refill refinement, it is challenging. Sometimes we don't get chi-square values good. So how we can improve or will that work, such materials, such biomaterials in DFT? And you also said that DFT is helpful in knowing the dielectric properties. So can we combine can we compare the one we are getting with DFT and one with spectroscopy and terahertz? Is it possible? And how we get? I mean, will there be a drastic?
Third one.
One question. And I want to know which softwares you will suggest for refill refinement. Which one is better and easy when it comes to biomaterial, like naturally occurring calcites, organoids?
Okay, please sit down. Okay, so out of 3 questions, 2 questions should be asked from the experimentalist. Fine. Anyhow, so I try to give the answer. Well, when I said I need the CIF file, experimentalists provide us this CIF, crystal information file. And if you want to publish a particular paper in a hi-fi journal, which is having a very high impact, definitely, whether you are experimentalist or theoretician, you have to give your CIF file. You have to give CIF file, and I have to give the structure file or postcard, whatever it is. In fact, it is CIF file. Okay, so definitely I already said in my slide, biological system are challenging if you can identify what type of molecule it is, and you can design your CIF file for that. Only in that case, you can run the DFT calculation for that. Okay, so means if you have the information about its CIF, only then you can touch the DC function theory. And about the ritual analysis, definitely we are having the many softwares and all are doing good. So for example, I think you are using Foolproof and Retica is there. So many softwares are used. Okay, which one? Okay, anyhow, high score is there. So you can cross-check with 2 or 3 software to try to design your CIF file in such a way. So if you are getting the similar type of the results, you can focus on that one. Right. Second question is related with the optical properties. See here, when we say optical properties, so this means we have to excite our electron from ground state to the excited state. Only in that case we can have the optical property. So density functional theory is a ground state properties, gives you the exact ground state properties. And for the optical properties, whether it is absorption, whether it is optical conductivity, whether it is the, what do you say, dielectric properties, constant, or the whether it is real part or imaginary part, all are the excited state properties. DFT can give the information about that, and I have shown you that my results are matching with the some of the experimental cases also. Okay, so means optical properties you can definitely touch. So you design your material and find the dielectric function. Okay, plot the real as well as imaginary part and give the work to the person who is engaged in the density functional theory. He will also predict the similar type of uh, uh, the dielectric response, whether it is theory, whether it is real part or imaginary part. And both are important because that both real as well as imaginary part gives you information about the spectroscopy. Okay, so I think this is sufficient. Whatever you want to ask.
Thank you so much. Sir, I request everybody to join for a photograph before lunch.